Hello everyone, this is Connor with the Aerospace Engineering Fellows. I'm back with another video. This is Prandtl lifting line theorem, and let's jump into it. So, Prandtl lifting line theorem is let's make some room here. Okay, let's make some room here. Okay, so this is a method we use for analyzing finite wings, right? So this is stuff like induced drag, right? Wing efficiency, induced angle of attack, AOA. We have a video on finite wings in general. You can check that out. Brush up on kind of the difference between an infinite wing and finite wing, what changes. But with that, let's talk about how we're analyzing these, right? So usually what we use Vortex Filaments, right? So what I have drawn here is essentially it's like a 3D vortex, right? So we started out, vortices were just, these planar guys, and essentially we've just stacked them up and put them in a line. All right, so with that, what we do is we twist them around and we shape them into horseshoe filaments, right? So this is horseshoe filament, right? And you can see that I've kind of drawn the direction that we've put them in right here, and this gives us a nice little, we have kind of a wingtip vortice-esque swirl on this side and the same on this side, and then we have kind of like a similar, whenever we draw vortex sheet, sometimes we like to approximate, or we like to use vortices. A vortex sheet, where we have kind of a similar thing going on right here, right? So with those, I'll erase this because I don't like that drawing and it's messy. So this is just one horseshoe filament, right? And this is really not good enough. One, because it implies that we have this like cusp, or not cusp, but we have this discontinuity where we have like circulation, and then no circulation, and then zero circulation, right? So this is, I've drawn gamma as our third dimension up here. So we have this like we have this discontinuity here, which is no good, right? So we stack some more up, right? And this time we've added, so you can kind of see I've tried to keep the direction of motion. Essentially we've done something like this, right? This is how we've lined up our horseshoe filaments, right? And we're just adding more up, right? And we end up with kind of some more like this, and we add more and more and more, and we end up with something that's nice and smooth, right? We have, a nice smooth drop off to zero for our circulation on both ends, right? And just in case it wasn't clear, I tried to make sure that, for this diagram, this is not the trailing edge of the airfoil I've driven. This is the trailing edge of the horseshoe filament. This is the leading edge of the horseshoe filament. Keep that in mind as we go, right? So we end up with something smooth, and we have gamma as a function of y being our span-wise direction, right? And so with this gamma of y, we don't want to show the goods too quick. With gamma of y, we can find w of y, right? This is if we have v is uvw, w is the z component, right? So our velocity is uvw, w is our z component. This is the downwash due to the lifting line, right? So in our other video on finite wings, we talked a little bit about kind of like the induced downward velocity that that pushes on our V infinity, right? I don't think I said this explicitly, but this is downwash, right? And so we go down here and we say, okay, yeah, because we like that, because that gives us alpha I, and if we have alpha I, the induced angle of attack, we can know how much of our original lift got tilted into induced drag, and that's an important quality. Or quantity. That's what we want to know, right? And when we do this, we get a nice big equation, which we love, which again relates back to that relationship where I really just, I'll reference you back to our finite wing video, but alpha GO is equal to the effective angle of attack plus the induced angle of attack. And what we've done here is we have another Fourier expansion. So these are, I guess these aren't together, but this is a Fourier. This is a Fourier. And you'll note that we don't have just some, so I say another because we also saw Fourier expansions in the thin airfoil theory. And we don't really have equations for AN anymore. What we have to do now is we have to evaluate this setup at different theta naught, and we'll set up a system of equations where we've evaluated a few different parts. And you generally don't use an infinite sum when you do that. And I don't want to get into too much detail here because we have a much more organized video explaining this process on an example problem where we go through and we truncate the terms, we remove symmetric lift distributions, right? We want, we remove asymmetric lift distributions because we want something that's nice and symmetric like this, right? About the x-axis. And anyway, we can set up, we can find AN, and then with that we can use that to find things like we have all these other relations, right? Where CL is equal to pi A1 AR. AR is the, sorry, I'll make that AR the symbol AR, the aspect ratio, drag coefficient, which for us the drag coefficient is purely the induced drag coefficient. We're not modeling any other drag. And this is just CL squared over pi, pi AR 1 plus equals 2 to infinity. And you know what? Yes, n equals 2 to infinity of n AN over A1 squared. Then we also have our efficiency factor, which is 1 plus delta squared, all in the denominator. This term right here is delta. Right. This gives us some more information. This is just one of the many ways we analyze our finite wings. There's a few other ways you can look at it. There's a few different important effects that I think Professor Evans likes to make a point of. But we're going to have we're going to have a new lift slope when we have a finite wing. So CL is equal to A alpha minus alpha L equals 0. Because CL is no longer, just this, this is now a function of our aspect ratio, right? And so if we have a, long, thin wings, we have a different lift slope than if we had short, stubby wings. We also have and you know what, I have the equation for A right here. A is equal to A naught over 1 plus A naught over AR, right? So I'm not gonna, maybe I won't spoil it quite yet, but you can take a look at how aspect ratio can vary, as you vary aspect ratio, how does that vary your A? And here A naught is just 2 pi, that's just our thin airfoil theory. That's just our thin airfoil theory lift slope, right? I think that's all I have for this video. If you have any questions, please feel free to come by office hours, leave a comment, do whatever you need to do to get a hold of us. We'd love to talk to you about it. And if you have anything else going on in your life, right, we are here for you in all aspects of your engineering education career. We'd love to help you. You know, we hate to see you struggle, so please come by, please come talk to us, and that'll do it. Thank you very much for watching.